The topic today is the chain rule, but let's start off with a guessing game based on what we already know about derivatives, in particular, the power rule. What if I ask you to guess the derivative of this function? It's 3 times a function of x raised to a power. The power rule tells us how to take something times x to a power, but if you sort of generalize or guess based on what you know about the chain rule, what might you guess the derivative of this function is? One thing you might guess for the derivative is 12, which is 4 times 3. Write the base down and drop the 4 down to a 3. That's sort of what we do in the power rule. Is that right? It turns out that it's not quite right. It's off by a factor, and I'll tell you what this factor is and see if you can guess where it might have come from. It's off by a factor of 10x. Now that is correct, but can you look back up at the original function and guess where the 10x might have come from? I'm not going to say anything right now, but I'll come back to it. In the meantime, let's go to the next one. What if I ask you to guess the derivative of this function? Again, it's 2 times a function of x to the 3rd power. If you follow this same procedure for the power rule, you might say the answer is going to be 3 times 2, which is 6, base to the 1 less power, which would be 2. As before, that's not quite right. It's off by a factor. And it turns out that the factor it's off by is 2x plus 2. And that really is the correct answer for the derivative. Now, looking at those 2 examples, or maybe you've already figured out what you think it is, what might be the pattern here for what you have to add as a missing factor? And I think probably you've guessed by now. Look at the base of that exponent, 5x squared minus 1. What is the derivative of 5x squared minus 1? Sure, it's 10x. And then look at the base of the next one. What is the derivative of x squared plus 2x? Right, it's 2x plus 2. Now, we haven't proven anything by giving these examples, but it certainly highly suggests that we know how to do this now. Let's try another. If I give you f of x is 4 times the square root of the quantity x squared minus 1, and we've dealt with this before. You know before you can apply any of these derivative rules, you've got to change that square root to a 1/2 power. But in that form, it looks pretty much like the other two. It's 4 times a function of x to a power. So your initial guess might be just start using the power rule. That means you would take 4 times 1/2, and of course 1/2 of 4 is 2. Write the base down, and then subtract 1 from 1/2. 1/2 minus 1 is minus 1/2. As before, that's not quite right. There's a missing factor, and if you follow along with what we've done before, you're probably going to guess that the missing factor is the derivative of the base, the derivative of x squared minus 1, which would be 2x. And in fact, that is correct. Again, we haven't actually proven anything, but it's highly suggestive that we've got now a new derivative rule that allows us to take the derivative of a number times a function of x to a power, whereas before we could only take the derivative of a number times x itself to a power. So looking at those 3 examples and realizing that we've sort of figured out what we think the pattern is, let's go into the formalities, because we haven't even started the formal discussion of this yet. But if you understand what we did here, you're well on your way to doing well on understanding what we're going to call the chain rule. So let's go through the formalities now. As you may have guessed by what I've alluded to so far, the generalization of these examples is called the chain rule. And actually, the result below is more properly called the general power rule, and I'll show it to you in a minute. But the result that I will be showing you below is more properly called the general power rule. But for our purposes, the kinds of problems we'll be working, we can really use those two terms interchangeably. We can say the chain rule or we can say the general power rule. For our purposes, it won't matter. And this is what it is. The chain rule, or if you'd rather call it the general power rule, says if we let u be a function of x, where f is a differentiable function of x, then the derivative of a number times u to a power is the power times the number, just like the old power rule, times u, the original base, raised to the 1 less power, which would be n minus 1. And then you have to multiply by the derivative of the base. Remember, this missing factor is the derivative of the base. If the base is u, the derivative is u prime. And there you go. That's the chain rule, or what we can also call the general power rule for our purposes. I just want to work a lot of examples because that's really it. So let's start with this one. If I ask you to find the derivative of the function y equal the quantity x squared plus 1 to the third, it looks almost exactly like the ones we've been working before. And remember, there's an understood 1 here. So the power rule, if it were just x, tells you that you multiply the exponent times the power. But now we say that the general power rule tells us we can do the same thing. So you're going to take 3 times 1 and get 3. You're going to drop the power down to a 2, but you're going to leave the base the same. So whatever the base was in the original, that base appears in the derivative too. But you're missing a factor, and that factor is the derivative of the base, which we're calling u here. So you've got to take the derivative of x squared plus 1, which is 2x. And of course, 3 times 2x is 6x. Simple, once you understand what you have to do. It's just like the power rule, except we've generalized it for the case where the base is more complicated than just x. And it requires you that you multiply by the derivative of the original base. Let's do another. Find the derivative of y equals the cube root of the quantity x squared plus 4 squared. Now that has to be changed to a fractional exponent before we can apply any of these derivative rules. We'll still be using the chain rule, but we have to change that radical into a fractional exponent. A cube root is a 1/3 power, but when it's the cube root of something squared, it's the 2/3 power. The index of the radical always goes into the denominator, and the power always goes into the numerator. So how do you do it? Well, you take the 2/3 and multiply it by the understood 1 there, and you get 2/3. Then you write the base down, which is x squared plus 4. Then you subtract 1 from 2/3. 2/3 minus 1 is 2/3 minus 3/3, which is negative 1/3. But then you're missing a factor. The general power rule says then you have to go back and multiply by the derivative of the base. And the base is this u, which in this case is the x squared plus 4. Derivative of x squared plus 4 is simply 2x. And if you want to clean that up a little bit, you can take the 2x and multiply, which is like 2x over 1, by the way, and multiply it by the 2/3, and that gives you 4x over 3, or 4/3 x, times the quantity x squared plus 4 to the negative 1/3 power. Now you have to play around with WebAssign and see what form you can leave it in so that WebAssign accepts your answer. You don't necessarily have to simplify it as much as I do in order for WebAssign to accept the answer. But that's something that you need to play around with on your own and get used to the way that you want to put your answer in as much as you want to simplify so that WebAssign does accept your answer. And you need to practice this. It doesn't necessarily stick after 1 or 2 tries. You need to practice, 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 because this is going to be extremely important for taking derivatives from here on out. How about this one? Same idea, except the u is much more complicated. The u itself, the thing you're raising to a power, is a fraction. So we know we're going to start off doing just what we've done before. Remember, that's an understood 1. So the power rule would say you take 2 times 1 and you get 2. Then you would write the base down. So you write the entire fraction back down again. And you reduce the power from 2 down to 1. And of course that 1 doesn't have to be written. It's an understood 1, but I put it there just for emphasis. But then you're off by a factor, and the factor you're off by is the derivative of the base. And I'm just going to write it symbolically. U prime is the derivative of the base. But think about it. The base is a fraction or a quotient, so to take the derivative of that quotient, we have to go back and use the quotient rule to take that derivative. So the answer is going to be, just copy this part of it back down again, and then use the quotient rule. The quotient rule is high d low minus low d high over low squared. Low being the denominator. The denominator is x squared plus 3x. The derivative of 3x minus 1 is 3. Then over here you write down the numerator, which is 3x minus 1, and you multiply by the derivative of x squared minus 3, which is 2x. And then you put that all over the denominator squared, which is x squared plus 3 quantity squared. And then you probably want to simplify it a little bit. Again, you can play around with what WebAssign will and won't accept, but I would probably feel a little bit better by simplifying it some. You can take the 3 times the x squared and the 3 times the 3, and you're going to get 3x squared plus 9. And then I'm just going to write that minus sign there down. You have to be very careful about not missing a sign. I'll use parentheses. And if you multiply 2x times 3x, you get 6x squared. That's this one. And if you take 2x times minus 1, you get minus 2x. That's that one. But remember, there's a minus sign there outside these parentheses. You've got to deal with that. So that means you have to distribute the minus sign. So that minus goes in and makes it a minus 6x squared. And then the minus times the minus makes it a plus 2x. And then, of course, you've got 3x squared minus 6x squared, which is negative 3x squared. And again, you might not have to take it that far for WebAssign to accept it. You need to play around with what you are comfortable doing with simplification. And if you get to a point where WebAssign will accept it and you're happy with it, then you can stop and put that in as your answer. You have to be careful. There's so many places with a problem that requires this many steps. There's so many places where you can make a careless mistake. Practice, practice, practice. It's very important. I will say, and I'm not going to go through this in detail, you could have also worked this problem by just going ahead and squaring the numerator and denominator separately and doing it like this, and then use the quotient rule that way. And you do high d low minus low d high over low squared. Again, I don't want to step through this step by step because I honestly think the other way is the best way to work it, but I did want to show you that it is possible to do it this way. And if you simplified it, you could get something like that. It's up to you to decide which way you want to do this. I actually prefer the first way I showed you to do it. But it's your call in the end. How about this one? Find the derivative of the function 4x times the quantity 2x minus 1 cubed. Now, if that x weren't there, you could just use the general power rule. But as it is, you've got two functions of x multiplied together. The 4x is one function of x. The x squared minus 1 cubed is another function of x. So this is going to be a product rule problem. So you've got to remember what the product rule says. It says if you want to take the derivative of a product, you take the first factor times the derivative of the second plus the second factor times the derivative of the first. So writing that down, you would have the first factor, that's 4x, times the derivative of the second factor. The second factor is a function of x to the power of 3, so you've got to use the chain rule. So you take the 3 down front, then you'd write the base down, you'd drop the exponent from a 3 to a 2, and then you'd come back and multiply by the derivative of the base, which is where the 2 comes from. And then continuing the product rule, the second part of the product rule says you take the second factor, which is the v, and multiply it by the derivative of the first factor. The first factor is 4x, the derivative is just 4. And if you clean that up a little bit, you can see that the 3 here times the 2 here gives you 6. And I would probably put the 4 in front just because it looks better. And then, of course, you can take 4 times 6 and get 24. And that's probably simple enough. And as I've said time and time again, and we'll continue to say time and time again, practice, practice, practice. This is extremely important. How about this? If Misha invests $2,000 in a municipal bond with interest rate R, written as a decimal, then the amount A that the bond is worth at the end of that time is given by this equation. Now, after having said all those words, basically all we're interested in is that equation. And the first question is find A prime. That's the rate of change of A with respect to R, but all they're asking us to do, in spite of all of the words they've thrown around at us, is to take the derivative of A. Go from A to A prime. Well, this is a perfect chain rule or general power rule problem. So all you have to do is change that. Well, you don't even have to do it, but I would suggest that you change this R over 12 to 1/12 R just for purposes of taking derivatives. Remember, dividing by 12 is the same as multiplying by 1/12. Dividing by a number is always the same as multiplying by its reciprocal, and you should feel confident in changing back and forth between those two things all the time, because sometimes it's better to write it as division, sometimes it's better to write it as inverting and multiplying. And I think in this problem it would actually be easier if you change that R over 12 to 1/12 R. You don't have to, you can do the problem without doing that, but I think it's just easier to take a derivative of a number times the variable than it is to take the variable divided by the number. Just my personal preference. But in this form, you can go ahead and take the derivative by the general power rule or the chain rule. It says you've got to take the exponent times the coefficient, write the base down, reduce the power by 1, and then come back and multiply by the derivative of the base. So that becomes 2,000 times 60. Write the base down, which is 1 plus 1/12 R. Change the 60 to a 59 by subtracting 1. And then you have to multiply by the derivative of the base. In other words, that's the U prime in the rule. I just wrote it symbolically, but that derivative is very easy. If you take the derivative of 1, you get 0, and if you take the derivative of 1/12 times R, you just get 1/12. The derivative of a number times the variable is just the number. We've known that derivative formula for ages now. And of course, if you want to simplify it a little bit, you can multiply the two numbers together, and multiplying by 1/12 is like dividing by 12, so either way you do it, you end up with 10,000 times the quantity 1 plus 1/12 R to the 59th power. And that's the answer to that question. I do want to ask a second question related to this, though. What is the rate of change if R is equal to 0.08? In other words, 0.08 is 8%, written as a decimal. All you have to do is plug 0.08 in for R and calculate. Now, just as I said earlier, I thought it was easier to take the R divided by 12 and write it as 1/12 R. I now think it's easier to take it and put it back. Again, you don't have to. You can do the calculation with it just as it is, but I think the calculation's easier if you just put it back the way it was. Multiplying by 1/12 is the same as dividing by 12. If you plug the 0.08 in now, I think you'll find it easier. You have to get used to using your calculator. I'm going to just leave this formula and talk about how to do problems like that. So let's just leave that particular problem right now and talk about the calculator usage. That power key, the X to the Y key, is what lets you raise a number to a power. For example, if I wanted to raise 4 to the 3rd power, I would type in the 4, press the X to the Y key, the power key, and then type in 3, and then hit equal to, and that would give me 4 times 4 times 4, which is what 4 cubed is. It's 64. That's how you raise a number to a power. It's also possible, and rather than doing it step by step and writing down intermediate steps, you can usually do this all in one flow in the calculator without having to write down intermediate steps. Remember, with this calculator, you don't have a programmable calculator where you can type everything in just just as it looks. You have to work a little harder, but it's not hard. So what you want to do to calculate something like, and again, I'm just making up an example. What if you wanted to calculate the quantity 100 times 1 plus 3/7 to the fifth? Then what you would do is you start, I like to say you start on the inside and work your way out. So you start with that 3/7. So you want to divide 3 by 7. That's this part, 3 divided by 7. When you press 3 divided by 7, the answer pops into the display right away. So now you want to add 1 to it. You divided 3 by 7, so now you want to add 1 to it, so it's plus 1. Now when you put plus 1 into the calculator, all you see in the display is 1, and that means it hasn't done the calculation yet. So you have to press the equal sign to make it do the calculation. So that's the next keystroke. Now you've done the entire base. You've done the 1 plus 3/7, so now you're ready to raise it to the fifth power. So that means you have to hit the power button, say that it's a power of 5, and again in the display you just see the 5 you pressed in. That tells you you have to press equal to for it to do the calculation. So as soon as you press equal to, it will do the base raised to the power. In other words, it'll do everything except times it by 100. So the last thing we have to do is times it by 100. And again, when you press 100, that's all that stays in the display. That tells you that it hasn't done the calculation yet. But pressing equal to will force it to do the entire calculation. And when you press that last equal to, you will get to the nearest cent, 594.99. In other words, $594.99. And it said to round it to 2 decimal places, so that's why I'm doing 0.99. Now, can you apply that to this problem? Well, sure you can. You take the same strategy, you start on the inside, the fractions, you take 0.08 and divide by 12. Let's get to that. So you take the 0.08 and divide it by 12. That's this. You can see that it did the division in the display, so you don't need to press equal, although it doesn't hurt anything to press equal. The next thing you want to do is add 1 to that, so you put plus 1. The 1 is still sitting in the display. That tells you that it hasn't done the calculation yet, so now you have to press equal to. That'll tell you the value of 1 plus 0.08 divided by 12. In other words, it'll tell you the value of the base. So now you want to raise it to the 59th power, so you press the power key and then type in 59, and the 59 just sits there. That tells you it hasn't done the calculation yet, so you have to press equal to, and that'll give you the result of raising that base to that power. The only thing you haven't done now is multiply by 10,000, so now you do times 10,000, and again the 10,000 is sitting in the display. That tells you that it hasn't done the calculation yet, so your last step is to press equal to, and when you do that and round it to the nearest cent, you'll get $14,799.79. You have to practice this stuff. You cannot just do it once and say, okay, I've got it. You have to practice. At this point, I just want to remind you, here are our tools for taking derivatives now. We already knew the power rule. We already knew these special cases. We learned the product rule, we learned the quotient rule, and now we've learned what for our purposes can be called interchangeably the chain rule or the general power rule. And that's what I call a toolbox. Those are our toolbox for taking derivatives. So at this point, you can use all those tools to take any derivative that you'll come across here. Practice, practice, practice.